All right. So there we go. I'm right now. My desktop. I don't have a wireless card set up into it right now because I've always had a hard line, and in the new house I don't have a hard line yet. I'm running a cable, but I just haven't had time to do that yet to run the cable through the ceiling. So in the meantime, I should be good now. I don't appear to be dropping frames at the moment. Hit play again. I restarted stream. Sorry, I'm just typing at the and I talk when I type sometimes. Anyway, sorry for that, but we'll go ahead and get started. So today we're going to be discussing algorithms, specifically analysis of algorithms, and we're going to get started today. But we're going to continue. This lecture goes both today and tomorrow. Or sorry, not tomorrow, but Friday. No surprise lecture tomorrow. Friday. There is no in-class activity for today, but there will be one for tomorrow. So do be aware of that. Is this a free lesson? This is actually a real college course. So technically, this is for students paying tuition. But that said, Twitch is a public forum. I don't mind if people watch. Um, so with that, just again the announcements that we're talking about today. There will be a quiz this weekend. Expect that. Um, and from there, this is a classic XKCD comic about Big O notation. Hopefully, if you don't understand this yet, you will later. No in-class activity today, but there is one Friday. There's not one Thursday. Sorry, I said tomorrow, and it's just because I think of each class as being one day after the other when it's not. So I did mean Friday. But yeah, I'm a huge XKCD fan. Anyway, the goals for this unit are to begin talking about data structures and algorithms, and to discuss the nature of performance. How do we actually measure performance in algorithms? And this is continued on heavily in 2150 and 4102, but we're laying the bedrock here. So you may be thinking, wait, isn't algorithms an entire course? Yes. Yes, it is a full course. We're not teaching that over the next 2 days. We're just laying a foundation for you to understand how we're going to do that. The first thing, before we talk about analysis of algorithms, is we need to talk about what an algorithm is. Now, I apologize in advance. Normally, you know I don't like teaching with slides. I much prefer doing live coding or the whiteboard that I have set up. But today is a very slide heavy day, so I kind of apologize in advance for that. But first, let's define an algorithm and define it in a very formal way. Um, so, an algorithm is a detailed step by step approach to solve a given problem. And an algorithm actually doesn't require a computer. There's kind of it's not a real quote, but people think it is, and people like it, so we attribute it to Dijkstra, who's famous for a particular graph algorithm. And the quote is that saying computer science about computers is like saying astronomy is about telescopes. It's not. Telescopes are the tools for astronomy, computers are the tool for computer science. But algorithms are a computer science topic even when they are taken away from computers, even when it's a human performing an algorithm. So the keys to an algorithm: steps are precisely stated in such a way that there is no ambiguity. Um, that is to avoid being interpreted incorrectly. The states are deterministic. If the system starts in a given state and you apply the algorithm, the end state is deterministic. Now, you can have randomness in algorithms, but that's generally when we talk about randomness with computers, computers actually aren't random. The math.random function that we've used earlier in the term isn't actually random. It uses the computer system clock, as well as it generates a seed from the system clock and doesn't. And so technically it is deterministic. It's just that it's really hard to set up the same state twice. Another key part of an algorithm, and this is actually important, the algorithm has to end. It has to terminate. Um, there are other properties that we strive for, things like correctness, that the algorithm produces the correct results, generalizability, that it can be applied across different scenarios, efficiency, etc. But those aren't requirements, those are things that we are seeking. So specifically, we're looking for unambiguous, deterministic, and ending. And by the way, I am monitoring Twitch chat, so anytime a question comes up, I will try to answer it. So how do we compare the efficiency of algorithms? Because the reality is not all algorithms are created equal. And how do we actually compare algorithms? That actually matters quite a bit. So um, let's first take a step back and start defining this term abstract data structure, because this is going to be relevant as we get what headset? Turtle Beach. Um, so let's keep questions please relevant to the class material. Thank you. Um, so with that, a data structure is just a way that we store information. So an array list, a map, a set, a tree set, I should say, or a hash map specifically. Those are data structures, and we tend to call these differentiate between concrete data structures and abstract data structures. All the data structures that we instantiate, array list, hash map, hash set, tree map, linked list, which we'll talk about today, those are all concrete data structures. They are data structures which are fully implemented. Each of those, however, implements something called an abstract data structure, and that is a model for how information is stored, but it's not actually storing information. Rather, it's a description of that storage. And the example that I would give is a list. So to that end, will the slides be posted on Colab? I thought I had posted them already, but if they are not posted, I will certainly have them posted at the end of the day. As I always post my slides in code, that certainly is not changing as we go online. If anything, I'm redoubling my efforts to do so. So let's take a minute and let's highlight some of the different data structures we've talked about. So the idea is we have these concrete data structures, and they're concrete like linked list, or we have array list, or hash set, or hash map, something like that. These are all concrete. Give me 1 second. Mods, can we please? And I apologize for this. Mods, can we please start deleting game related comments just because this is during class? Thank you. I'd be happy to answer those questions after, but I'm not going to answer the questions during class. Thank you. From there, we have this abstract class like a list. And linked list and array list both implement list. That is to say that the list defines an interface. And we've talked about that interface, how we have functions like add EE. And we have functions like remove, object O, or contains, object O. These are methods that are in the interface of list, and list is abstract. Pardon me. So the list in this case is abstract. We can't directly instantiate it. We cannot say list L equals new list blank. We can, however, and I'm going to pull up the screen share real quick. We can do things like we've done in the past, like this. List integer int AL equals new array list integer. Mods, please ban that user. Or at least time them out for an hour. Thank you. I apologize, everyone. This is one problem with doing it on Twitch. I won't be Mods, can we please step up some strictness here? I apologize, but the chat has gotten a little bit out of control. Thank you. So to that end, on line 13, why have we previously typed array list? I'm not sure what you mean. What I'm trying to illustrate is that an array list is a list, and so we could instantiate this in two different ways. We can say, for example, int al equals new array list like this. Or we could do this. Pick one. Both of these independently are fine. Obviously, we can't do both because we're defining the same variable name. But what we've talked about before is how we have inheritance structures, and because list is an interface and array list implements that interface, array list is a list. So this is an example of using abstraction. We have two lists. These two lists are different concrete data structures, but they are the same abstract data structures. Correct, there is no in-class activity today. So that's the idea here. And looking back at the whiteboard, we can do this because linked lists and array lists implement the interface list. That is to say, they realize lists. They create a concrete implementation. Any other clarification or people still confused about this, about why this is fine? List is an interface or parent class. It is actually an interface. Can you instantiate a list? No, you cannot, because it's an interface. Although you could not instantiate it if it were an abstract class either. But you cannot directly instantiate a list. And that's because the list is abstract. It's not implemented. It simply defines an interface. Array list and linked list are not abstract. They are concrete. So is there any practical difference? The practical difference is that when I treat this as a list, I can then combine, I can use a function that takes in a list can take this in and take this in, and it won't know the difference. So abstract data types are interfaces. Not necessarily. Abstract data types can be abstract classes, but in this case, with list, it's an interface, and with the Java collections framework, they tend to be interfaces. So first, let me explain what I'm doing here. What I have, all interfaces are abstract, correct. And all abstract classes are abstract, but remember that an abstract class means we can't instantiate it. So, to this end, I now have two lists, and I'm going to test these two lists. I'm going to insert 100,000 elements at the end of each list, and I'm going to time it. This function will time the process and print how many milliseconds this process takes. I'm then going to clear both lists. This is to empty them. And I'm then going to insert at the front 100,000 times. So think of this like doing just a test to see which is faster, array list or linked list. I'm then going to clear both. I'm then going to insert into a random position in the array list and the linked list 100,000 times. Finally, I'm going to randomly access 1,000 elements inside of the linked list and the array list. And the reason I'm showing this is I want to show you that the abstract data type defines the behavior. The concrete data type is actually where we determine how effective our algorithm is. That is to say, there are some places where an array list is significantly better than a linked list, and there are some places where a linked list is better than an array list. And understanding where they're better is important. And just to show you this, I'm going to run this program. And as we take a look at the output, if I can get my mouse to, there we go. You'll see that both adding at the end, array list and linked list, took about the same time. Not really enough difference. But notice that adding to the front of a linked list was significantly faster than adding to the front of an array list. Further, when we add randomly, that means in the middle, and I'm going to move my face over here to be out of the way for a second. You'll see that it took over 13 seconds, 13 and a half seconds to insert. Sorry, this first one should be front. That is a here. I mean, it's just a simple typo, but just to avoid confusion, um, that's insert at end. This should be insert at front. So real quick, just rerunning it. So you can see, all right, sorry about that, fixed it. Wait, what's a linked list? A linked list is another way to implement a list. We'll actually talk about how a linked list works later in the class, but for now, just think of it as like Coke and Pepsi. Array list is Coke. It's more tried and true, more widely regarded. I personally prefer it. Linked list is Pepsi, which is to say that no one likes it. But in actuality, we will talk about how linked lists are implemented, and there are cases where linked lists are better. And specifically where a linked list is better is right here. If we're going to insert at the front of a list a lot, a linked list is better than an array list. Okay, but we shouldn't be worried if you're not familiar. Correct. You don't need to know exactly how a linked list works. All you need to know is that linked lists and array lists are implemented differently, and because they are implemented differently, they perform differently doing various functions. Excuse me. So while they're both basically the same amount of time, I will say that this 0.05 seconds is probably more related to just warm-up time than it is related to actually related to performance. That is to say that both adding at the end tend to perform about the same. Adding to the front of an array list is significantly slower. 375 milliseconds versus 5 milliseconds to insert 100,000 items. Does inserting at the front mean at index 0? Correct. And that's because when the array list, just to quickly illustrate why with an array list this is slow. With an array list, we actually do have an underlying array. And so let's say, for example, the idea of an array list is we have an array that has as much space as we need. Remember how we talked about expand if needed, grow if necessary with stacks and queues? Array list has a similar function. So it will expand if needed. But for now, let's say that I have the numbers in my array 6, 7, 5, 3, 0, 9. Now, if I were to insert 8 at index 0, Java's not going to just add an index here. It can't do that. What ends up having to happen for me to insert into the front of an array list is Java will automatically move all these elements over. And then after all the elements are moved over, so 9, 0, 3, 5, 7, 6, then we can insert the number 8. So this process is slower. Now, if we were inserting at the end, we could just put 8 there. But the point is, adding to the front of an array list is slower. Why is it faster with a linked list? We'll talk about that when we get to linked lists. Why can't it wrap like a queue? Array lists don't do wraparound. And the reason for that is just the array list is not the same as a queue. A queue can be implemented with an array list. The queue can be implemented with an array list, but by default, it's not going to just arbitrarily wrap around. And it's because the array list is designed to mimic a list, not a queue. So when adding in front of an array list is empty, so if it's full, the array list doubles in size, just like we talked about with a stack and a queue. And so it will double in size, and then it will insert at the front. So it still has to shift all the values over. By the way, I apologize. I seem to be dropping frames. Please let me know if it gets unbearable. The point being, this is why adding to the front of an array list is relatively slow. But now, let's take a look at what happens when we added a random location. That random location could be in the middle. With an array list, notice that it takes about half the time of inserting at the front. That's because on average, we'll have to shift half the elements. So it turns out mathematically that this works out pretty well to take half the time on average. But wow, look at inserting into a linked list in the middle. That took 13.8 seconds. That took almost, I mean, we're almost 2 orders of magnitude slower than inserting into an array list. So an array list should be used whenever you do access in the middle. Accessing a random element took 1 millisecond to access 1,000 elements in an array list. That is to actually get the element, the call on the get function. For 1,000 elements, it took over 2 orders of magnitude longer for a linked list. C++ is vector, so I'm not exactly sure how C++ vector is implemented. My understanding is it's implemented like an array list, so I would expect it to be slower. But I would, if I'm told I'm wrong on that, I wouldn't be surprised. Anyway, the point here, though, is this is actually what I just did, a bad way to analyze algorithms. And here's why. Over here, I have the same program on my laptop, the exact same program. I'm going to fix the same bug I had before real quick. But my laptop, of course, is a different computer. And what I'm going to do real quick, apologies, is I'm going to try and see if this will work. Yes, linked list Dan's game indeed. I completely agree with you. As I'm going to try to show you what happens when I run this program. And I apologize if you get a little dizzy here. So notice this computer is slower than my desktop. Now that's not surprising, but it turns out to make a pretty big difference. As we're waiting for the middle run, notice that already we're slower 0.633 seconds than my desktop, which was 0.375. If you're not in the class, can you still take a quiz? No, you cannot. But 23 seconds, almost twice as long to run on my laptop. So the point here, and thank you for indulging me that, sorry for that. The point here is that every computer is different. And so when we're looking at analyzing algorithms, we care about runtime. Runtime really matters, but we actually don't care about the exact runtime. And that may seem strange. How do we care about runtime, but we don't actually want to be explicitly defining our runtime? Well, what we really care about is how quickly the algorithm grows in complexity. So I actually have, if you go on Colab, that list analysis program is on the website. It has that same typo front end, but you can run that on your computer, and I guarantee you'll get different times. But here are some things that I will absolutely guarantee. One, by far, this, inserting randomly into the middle of a linked list, will be the slowest thing. By far. It won't even be close. It will be significantly slower than this. I will guarantee that an array list, inserting at the front, will be slower than a linked list, but it will still be a bearable amount of time. Pardon me. And I guarantee accessing this time will be incredibly short, and this time will be significantly longer. And the reason for this is because of the order of magnitude of the algorithms. And we're going to talk later today and into Friday about some terms like constant time, log time, linear time. Understand that when we're discussing that, we're talking about the algorithm. We're not actually talking about code even. We're talking about the algorithm, because code is just a formalization of an algorithm. It's just making an algorithm work on a computer. But the algorithm is independent of the code, and algorithms themselves can be inefficient or efficient. So let's head back to the slides for a bit here. And so again, we were talking about how when we're talking about how algorithms are analyzed, we're talking about algorithms within concrete data structures, not abstract data structures, because abstract data structures don't actually implement the solutions. They just say, hey, these are the solutions that are available. Excuse me. So as a result of that, Java interfaces generally match abstract data types. Interfaces don't have data fields, but they do have various functions and features, and the lists implement those. So we talked about the efficiency or performance is often the major consideration. So for example, if I need a list, if I'm trying to create a list for some algorithm that I'm using, I need to consider how I'm using that list. For example, if I'm likely to add at both the front and the back, but I will never add anywhere in the middle of a list, that's actually a time I will use a linked list. But if I need to access any values in the middle or add anywhere in the middle, an array list will always be faster. Okay, that user needs to be banned permanently. You didn't see that message chat, so don't worry. Anyway. So with that, please, again, I know that this is all haha funny that I'm on Twitch and everything. I'm actually trying to teach my class, so please be respectful. Can you explain the Mike-Oxlong theorem, please? No, I cannot. You were already timed out, so I'm just going to time you out for the remaining hour. Thank you. Um, any real questions? Yeah, I'm going to do that. Can you explain what an ADT is again, real quick? An ADT is an abstract data type. So going back to the whiteboard, the list describes a set of features, add, remove, contains. But the list interface does not implement those behaviors. It only specifies um, what those behaviors are, the interface of them. So the name of the function, the inputs, the outputs. Those are abstract because we cannot directly instantiate a list because it's not actually implementing anything. It's just describing the behavior. Linked list and array list are not abstract data types. They are concrete data types. They are implemented in the sense that the functions actually are implemented in a specific way. Any other questions? Or does that... Okay, good. All right, just wanted to make sure that you got it. Thank you. All right. So now, why don't we just time our algorithms? So how's an abstract? So an abstract data type is a specific type of interface. That is to say that some interfaces, I would say, are not. Some abstract data types may be implemented not as an interface, but as an abstract class. That's possible as well. But an abstract data type kind of goes beyond Java. An abstract data type is not a Java term, whereas an interface is a Java term. So it's kind of a bigger umbrella. It's I was about to say more abstract, but that wouldn't be helpful. It is more broad than that. So again, why don't we just time the algorithms? Because everyone's computer is different. And the reality is computer hardware has changed incredibly rapidly. Um, if this program takes right now 12 seconds to run on my computer, well, if I wait a few years, upgrade my processor, upgrade all my memory, things like that, maybe now it only takes 6 seconds. Or maybe even less time. So that's why timing isn't valuable. But what is valuable is to look at how the algorithm grows. So first, understand that I'm focusing a lot on time. Efficiency is not just time. Efficiency is the idea of if we take a problem of size n, what would be faster, hardware or software? I don't understand the question. Forgive me. Hardware and software work together. They don't compete. What's the difference between hardware and software? Hardware is that. That is my hardware. Right there. That is the physical system that is running my computations. Software are programs like PowerPoint here. This is software. So the hardware are the physical components that run a system. Software can be optimized. Yes, it can be. And we're talking now about how we optimize software. And we have to focus on thinking about efficiency. And so we focused mostly on time. That is the amount of time it takes to process something. And that tends to be what we think about. Understand that we can also measure efficiency in terms of memory usage, in terms of disk usage, which is generally much slower than memory usage, in terms of network usage, how much bandwidth the program uses, etc. And to that end, when we're measuring efficiency in these different ways, we're trying to reduce time, memory usage, disk usage, network usage. We want to use less resources. And again, time tends to be the most interesting because hardware has grown to the point where, you can do billions upon billions of operations per second. I shouldn't say billions upon billions, that implies billions of billions. It's not that, but you can do several billion operations per second now. So really, we care more about time than anything. Memory is also pretty cheap right now. So, to that end, when we're measuring efficiency, we are measuring efficiency with respect to some n. N, in this case, is the size of our input. So, for example, if, and I'm just going to go over to the whiteboard here real quick. Here, we talked about how to insert into a front of an array list that was size 6, now 7. So this took 1, 2, 3, 4, 5, 6 moving steps and then one copy step, copying the 8 into here. So total, that took 7 steps. And I'm defining steps very broadly, and we'll talk about why I can get away with defining steps so broadly. But now imagine that instead of an array list of size 7, I maybe had an array list of, let's say 300 million. How many steps would this take? Would this take 7 steps? No, to insert at the front, I would have to shift 300 million values and then 1. So notice that this becomes 3, 1, 2, 3, 1, 2, 1 steps. So notice that when I increased the size of the problem, inserting at the front, again, that's the focus, the number of steps grew. And the number of steps that it takes, sorry, I'm blocking the camera, and the number of steps that it takes to perform this insert at the front is the size of the array. I have to shift n values, so we're calling this n, which initially is 300 million, plus 1 to actually insert that last value. Here, I had an array list that was size 6, and it took 1 additional step. Oh, sorry. Yes, correct. You caught me there. Sorry, I wrote the wrong number of zeros. Thank you for catching that. Oh, camera down. Fixing. Sorry, I will fix that. Let me. We have a problem. I'll fix that later. Sorry, I will. For now, hey, you can see Colby on the couch there. Sorry about that. I will fix that later. The point is, the amount of steps the problem takes grows with the size of the array list when we're inserting at the front. No, that wasn't the cat. That was my chair. Sorry about that. Let me again try to fix this, and I'll more precisely adjust it later. Are you assuming the different steps take the same amount of time? I'm actually not, because I'm not interested in the amount of time. I'm interested in the amount of steps. Because the reality is, again, we're not interested in the specifics of exactly how much time each step takes. Rather, we're interested in how this problem grows. And what I found is that, and let me pull it back up, adjust it here. Sorry. There we go. What I found was that the number of steps that it takes is a function of n. The number of steps is some function of n. I'm getting really annoyed at my chair now. I'm going to have to reposition my chair here. Sorry about that. This is the problem with not having a wireless camera. Sorry about that. See if I can get the camera to refocus. There we go. So we're not interested in the actual runtime, but rather a broad implication of how much the problem goes. And what this tells me is this. Let's say I have a list of size n. If I have a list of size n, if I double that size, it becomes 2n. How much longer will this problem take? That is to say, if I'm inserting at the front of an array list, and let's say, hypothetically, the array list is size 1000, and inserting at the front took 100 milliseconds. I could assume that the runtime will roughly double if I double the size of the list. If I double the size of my input list, inserting at the front will take twice as long. Does that make sense? And you've probably heard this expression in the news, but we're going to refer to this sometimes as doubling time. And the idea of the doubling time is if a process takes n steps to do something, if I double the size of the input, it now takes 2n steps. So now, why don't we get into the specifics of the runtime? It's because we're not actually interested in calculating a precise runtime. Rather, we are interested in calculating the growth. That is, as n increases, how much slower will this take? And there is slight limits. That's actually not explicitly accurate. We'll talk about this tomorrow, but specifically, that is a more accurate representation, 2 to the power of n of exponential. Bubble sort is not exponential. Bubble sort is polynomic. And we'll get into the difference between the two. If not today, then certainly on Friday. So when we're talking about the rate of growth, we're broadly defining steps. And we can actually be a little bit loose with this. We don't need to count the lines of code exactly. Rather, we're interested in how many independent procedures need to be run. And to that end, this is where we kind of cheat a little bit. Because let's say, and I'm going to pull up my notepad here. Let's say, for example, we have 2 algorithms. We have one algorithm that takes the number of steps is equal to 2n, and the number of steps is equal to 3n. We actually don't consider these algorithms as different. We consider them the same. And that may seem weird, but here's why. This program will run twice as fast if you wait 18 months for better computers. So we really don't even care about the coefficient of n. Rather, we care about the fact that this is n, as opposed to something like n squared, or n cubed, or log of n. And we'll get into the differences between these, but we actually don't really care about the difference between these two. And you may be thinking, well, why don't we? That coefficient seems important. It's not that we ignore it. The coefficient does matter. Certainly, if this were an accurate representation of the runtime, this would be better. But this is why we play a bit fast and loose with steps, because we're really interested in this number. And here's why. If a procedure takes n squared, proportional to n squared time, most recursive algorithms, some recursive algorithms are even better than n squared. We'll talk more about different algorithms as we go. Each algorithm has to be evaluated independently. But to this end, what this means, if something is n squared, if the number of steps is n squared, then if we double the input, it's not necessarily, because keep in mind there could be some other limiting factors. Again, we don't really care about 2n or 3n. We care about n. And the reason we care about this is if I double the size of my input, if I double n, let's say that n is initially equal to 100. So f of n equals, and that's going to be 2 times 100 squared, that's going to be 20,000. Or f of n equals 30,000. If I double n equals 200, now the first, and I'm going to, just to clarify, f of n now equals, and I can tell you this without even doing the math, it's going to be equal to 80,000. And g of n is going to be equal to 120,000. It's going to take 4x as many steps. So let me expand this a bit. We're talking about the rate of growth. So notice this, when I'm dealing with n squared, if I double the size of the input, the runtime or the number of steps increases by a factor of 4. So with n, double takes twice as long. With n squared, double takes 4 times as long, roughly. Again, I'm being very general here, not exactly. With n cubed, it's going to take, n cubed, it's going to take, in this case, 8 times as long. And so the coefficient ends up not mattering all that much, because keep in mind, both of these, when I double the size of n, increase by 4. It doesn't matter that this was 2n and that was 3n. They both, when I double n, increase by a factor of 4. The coefficient, I'm not saying the coefficient can depend on the hardware, but rather that, again, we're not, understand, and I'll repeat this again, we're not trying to get an accurate runtime estimate. We're trying to get how much the runtime grows as n grows. So is 0.5n faster than n? Sure, but we actually don't really care, because when they both double in size, they both do that. So this is why, again, the point here is to free us of trying to understand this specific exact runtime. That's not our goal. We're interested in the growth. Focus on the growth, not on the exact runtime. Because it turns out that let's consider two different algorithms. F of n equals 100 times n, and g of n equals n squared. Let's say I had these two algorithms. Which is better? Now you may be thinking, well, depends. This number, if n is small, this is going to be worse. But it turns out we don't care, because what we're really interested in is when n is really big. And when n is really big, this is going to be better. Again, I'm just describing if this were an estimate of the number of steps. We're not trying to explain what this algorithm is. Don't get caught up in that. Focus on the idea of growth. If you're thinking seconds, your mindset's in the wrong place. If you're thinking, what does this code do? Your mindset's in the wrong place. For now, just focus on the rate of growth of the steps. And this grows slower. And that's why we say it's better. Even though if n were less than 100, this is slower. Exactly. It really is about the rate of growth, not about the explicit runtime. Because the thing is, the runtime will follow the rate of growth. So this is how we're going to think of our algorithms, as each algorithm takes a set number of steps. And so we need something to count. That thing we count is going to be steps. Exactly. I'm looking at how the program scales with input size n. So, if n becomes 100, these two runtimes are equal. But if n is 1,000,000, this algorithm will be 10,000 times faster than this one. How would you find f of... So again, I made these up. We'll talk about how we go from an algorithm to the rate of growth tomorrow. But I want to at least just introduce the idea that we can measure something. So generally, for example, if code has a loop that loops n times, it's at least O of n, and we'll talk about what that means tomorrow. But for now, I just want you to think of the mindset of rate of growth. That's the emphasis here. So from there, I'm just going to quickly, when we're counting operations, we want to focus on an algorithm's critical section. And here's what I mean by this. So let me look through the code. If you'll notice here, in this code, this is a bad example. Let's look at the grow if necessary function. In grow if necessary, what line of code, and this is not hypothetical, which exact line of code runs the most times? If I call the function grow if necessary and assume we actually enter the if statement for now, which line of code runs the most times? So 49, line 50. You could argue that technically this is a line of code because this is a check, this is a line of code, but it's these two things are going to run the most times. Please, when people say things like that, do not time them out, block them, ban them permanently. Thank you. That when it's something like that, there's nothing the student is or the person is contributing to the class. So please ban them permanently. I did ban him, but I did see a timeout. So I just wanted to make sure that precedent is set. Anyway, I did personally ban him permanently. Anyway, apologies for this, everyone. So from there, when we're measuring the steps, let's actually count the number of steps. Let's assume for now, assume we enter if statement. And let's just cheat a little bit. And let's say every line of code is one step. That means that line 48 is one step. Line 49 technically is a loop, but we'll say initializing is one step. And then the length of my array, that's how many times we're checking this condition. So that's going to be plus n. And then I++, we're going to do n times. So that's plus n. Again, you're right, we want a slower rate of growth, so that is better, correct. Now, this line of code, this only takes one step, but we're going to do this step n times, so it's 1 times n. From there, we have 4 more steps. Each of these steps takes 1 time. Now, I did this very, very broadly, but the point I can show you is I can now add all these together, and I can say that this is 1 plus 1 plus n plus n plus n plus 4, or 3n plus 6. And again, you may be thinking, well, can we get this down to 2n, or maybe get this down to plus 5? We actually, at a broad level, and we do care, I want to be clear, micro-optimization is not a bad thing. But again, the emphasis here is this value n. We don't really care about the 3, and we don't really even care about the 6. What this tells us is that, again, if n doubles, the runtime roughly doubles. That's what we're focusing on here. This came from line 50. Specifically, this statement only takes one step, but we run this line of code n times. We get this from line 49, and this is because we only create I one time, but every time in the loop, we have to check our exit condition. That's one step, so we do that n times, and every time through our loop we do I++, so we do that n times. So that's where that comes from. Right, so a loop within a loop can be inefficient. Now, there may be some problems that can only be solved by a loop within a loop. And there may actually also be some problems that can only be solved in O of 2 to the power of n time. And this is exponential. And I want to be clear because this is, and I apologize, I'm running out of time, so I'll wrap this up and then I'll stick around to answer more questions later. Exponential. This is what exponential is. This is not exponential. This is quadratic. And trust me when I say this is substantially worse. Exponential is horrible. It's really bad. But it turns out that there are some problems that we don't have better solutions than this. That all of our solutions that exist take exponential runtime. And this relates to P versus NP. If you've ever heard of this, P is polynomic. Polynomic. That is to say, the runtime can be expressed as a polynomial, where everything is n to a power, as opposed to non-polynomic. And this means exponential. And some examples of this are the traveling salesperson problem or the knapsack problem. If you've ever heard of those are considered NP. And near as we can tell, there may not be a polynomial solution to those problems. If you ever find a polynomial solution to those problems, congratulations on your Nobel Prize that you will win. What is the letter O you're looking at? So we'll talk about this tomorrow, but this relates to something called the order of magnitude. So with that, I'm going to just answer questions. I'm not going to introduce any new concept. I know I've already gone 4 minutes over, so if you have to leave, you can leave now. From here, I'll just answer any questions about today's material. I won't introduce new material. Is there such a thing as sine of n? I am not familiar with any algorithms that take sine runtime. Sine of n would actually be constant time, because the sine of n produces a number between -1 and 1, and so this would be a constant value. You could just say 1 is greater than sine of n, so this would be something called constant time, which is to say we assume the procedure always takes the same number of steps. How do you find an n on each line? So I went over this again. This is the last time I will go over this for the sake of time. The reason we say these steps take n time is because we are looping from 0 to the length of the array. And we're defining n is the length, not of the array, excuse me, of the list. We're defining n to be that because that's the size of our input. So this loop is going to runs n times. This statement will only be executed one time when we first start the loop. This statement will be executed every time we step through the loop, so n times. This will take n times. This statement by itself only takes 1 unit of time, but we have to do it n times. So that's where that comes from. Again, we'll actually talk about big O notation on Friday. I didn't really get into it. Can call this a preview of Friday, a sneak peek, a trailer for Friday, and we'll talk about what it means then. Can you go back to abstract data type versus if I have time? I have to get onto a meeting at noon. Let me just check the other questions because I reiterated that I think 3 or 4 times. So I'd actually just ask that you go back and watch the recording, just because I unfortunately don't have the time, and I do apologize for that. But you can go back and watch that. Are we going to go over how to determine fast, slow, hour, like how to find n? So remember, n is the size of the input, so we don't find it. Rather, we find the runtime with respect to n. But we will talk about that. We'll talk a little bit about it Friday, and then we'll again talk about it on Monday. I am going to link, and this is, I want to be clear about this. This is not required to watch. But I'm going to link Minecraft Universe Death Clock. And I encourage all of you, and I'm going to link this in chat. I'm not going to show it on stream because copyright issues. I want you all to watch that video because I want you to realize what exponential means. Exponential is beyond what we're naturally capable of really understanding. That video is really cool. It's also depressing. It's really depressing. But it's a very cool video if you want to understand exponential growth. That video is great for it. With that, I'm going to end the lecture today, and I will see everyone Friday. I do have office hours tomorrow. Again, they are in Discord. All that information is on the Piazza Master thread. I do have to get on a call. Normally, I'd be willing to stick around a bit longer. I do apologize. But take care, everyone, and I will see you all Friday.